Welcome to NZERA Exam Preparation. This is the 2024 Advanced Level National Examination in Mathematics, Paper 2, set by NESA. It is a demanding paper, so we'll take each question carefully. For everyone, we understand what is asked, teach the idea behind it, and work a clear step-by-step answer. Let's begin. First, how the paper is built. It carries 100 marks over 3 hours, and a calculator is allowed. Section A is questions 1 to 15, all compulsory, worth 55 marks. Section B is questions 16 to 20, and you choose any 3, worth 45 marks. The topics span logic, algebra, trigonometry, calculus, series, conics, and probability. Let's start with Section A. Section A. These 15 questions are all compulsory. Let's take them in turn. Question 1. 2 true or false statements to judge. Part A says a binary operation combines 2 elements to give a unique third element. That is exactly the definition of a binary operation. It takes 2 inputs and returns 1 and only 1 output. So part A is true. Part B says a compound proposition that is always true is called a contradiction. That is the wrong name. A statement true for every truth value is a tautology. A contradiction is one that is always false. So part B is false. Question 2. Solve 2 log x equals log of x plus 12. Remember, logarithms only accept positive inputs. Keep that in mind for the end. Using the power law, 2 log x is log of x squared. Since the log function is 1 to 1, the insides must match. X squared equals x plus 12. Bring everything across. X squared minus x minus 12 equals 0, which factors as x minus 4 times x plus 3. So x is 4 or minus 3. But x must be positive, so we reject minus 3. The solution is x equals 4. Question 3. The polynomial p of x equals x cubed plus nx squared plus 3x minus 1 leaves a remainder of 1 when divided by x minus 2. Find n. By the remainder theorem, the remainder when dividing by x minus 2 is just p evaluated at 2. So p of 2 is 8 plus 4n plus 6 minus 1, which is 4n plus 13. Setting this equal to the given remainder 1, 4n plus 13 equals 1. Then 4n is minus 12, so n is minus 3. Question 4. Given tan a equals a over a plus 1 and tan b equals 1 over 2 a plus 1, prove that a plus b is pi over 4. The plan is to compute tan of a plus b and show it equals 1. The addition formula gives tan a plus tan b over 1 minus tan a times tan b. Putting the numerator over a common denominator gives 2 a squared plus 2 a plus 1 over a plus 1 times 2 a plus 1. Working out the denominator gives the very same expression, 2 a squared plus 2 a plus 1 over the same product. So the ratio is 1, tan of a plus b is 1, which means a plus b is pi over 4. Question 5. 2 curves, f and h, are drawn, and we must state each period and one difference. The key idea is that the period is the horizontal length of one complete cycle. The distance before the curve repeats itself. To read it, pick a feature, say a peak, and measure across to the next identical peak. For the difference, look at whether the curves have the same height and shape but are slid horizontally, that is a phase shift, or whether one rises higher, which is a difference in amplitude. Read the exact periods straight off the marked axis in your paper, then describe how the 2 graphs relate. Question 6. Solve 3 cos x plus 3 equals 2 sine squared x for x between 0 and 2 pi. We can't mix sine and cosine, so replace sine squared x with 1 minus cosine squared x. That turns the equation into 2 cosine squared x plus 3 cos x plus 1 equals 0, a quadratic in cosine. It factors as 2 cos x plus 1 times cos x plus 1. So cosine x is minus 1/2, or cosine x is minus 1. Cosine minus 1/2 gives x equal 2 pi over 3 and 4 pi over 3. Cosine minus 1 gives x equal pi. so the solutions are 2 pi over 3, pi, and 4 pi over 3. Question 7. Find the domain of f of x equals the natural log of e to the x over 1 minus e to the x. A logarithm is only defined when its input is strictly positive, so we need the fraction to be positive. Now, e to the x is always positive, so the top never causes trouble. The sign is set by the bottom, 1 minus e to the x. We need 1 minus e to the x greater than 0, that is e to the x less than 1. Since e to the x is below 1 exactly when x is negative, the domain is all x less than 0, minus infinity to 0. That brings us to the end of Part A. The paper continues in Part B. Open Part B next and keep going. We pick up exactly where we left off. See you in Part B.